Hi everyone. I'm back after taking a little bit of a break. Wasn't much of a break, but as you can see, I have pretty good drawings right here now. So I've gotten really used to this program now, and so the drawings will be a little bit more lifelike. Of course, a stick person isn't necessarily like lifelike, but the stick person has actually improved too. So, but anyway, for future videos, I'll try to make it a little bit more realistic so you can visualize a little bit better. But if it's if I gotta just turn out a little bit more videos, I gotta turn out more videos, I guess. But I'll try to make it a little bit more lifelike right now. Sorry about the previous videos. They're lacking color, I guess. But maybe one day I'll revise them. But for right now, let's just move on. But yeah. So for future videos, they'll look a little bit more like this. So actually have a spring actually drawn right here. So that took a really long time, but now I'm starting to have an archive of things, so it should be a little bit easier of making objects. But anyways, so this video, as you can see from the title, is how do scales work in the end? So basically, scales work by just springs in the end. So as you saw with the last video, we had our normal force, and then we also had our weight, nothing else. So what we're going to be doing now is actually introducing our spring force. So really, I'm just going to say that's K delta X. So for all my springs forces, I'm just going to use this, really. Or I might use this, but in the end, the formula for a spring is just F equals, or actually if you want it in vector form, your force vector is equal to negative K delta X, your delta X vector. So really, if you're displaced down by this much, your force is going to be up, is really what it's saying. So I'll probably, for future reference, don't include this negative when doing this. Just think if it's getting compressed, then like the force is going to go up. So really, like if we look at this plate, it's going to have a K delta X up. So I'm not going to write negative just because it's that it's already in the right direction. But yeah, so this is going to be X in the end, and let me just erase this guy. Okay, so anyways, yeah, so really, if we have two springs right here, and they both have basically a stiffness of K is just a constant in the end, and K is typically measured in a laboratory ahead of time. So since it's a constant, it's always going to be that unless it's deformed. And once you know that, that can be used wherever, essentially, So really, for this problem, we know this in the end, and typically you'll always know this, or just be given that in your problem. But yeah. So anyways, so we have two forces, two springs right here, and they're gonna have two forces being applied, just to counteract this person's weight. So in the end, so it's not vector. Well, it is a vector, but yeah. So in the end, so let's just look at this person real quick. So they are going to have a normal force going up, and they're also going to have a weight going down, so which is just mg. So now this normal force is going to be equal and opposite onto this plate. So it's just going to be like that. So so anyway, so if we do the sum of forces for this guy real quick, so sum of forces in the y direction, it's going to equal n minus mg, and since it's a static problem, it's going to equal 0, and so then n equals mg. So n is equal to the weight of the person. So which makes sense. This has to be a static problem, because why would you measure a weight of a person if you're like in a car or in an elevator? It would be off, and a lot of times it'll just show up as an error or something, it's already written in the I get in the code of the calculate not the in the scale, you know. So but anyways, so really we know the normal force is going to equal mass times gravity for this case. So like I said, this isn't always true. Figure it out from here, you know. But yeah, I'm done talking about that. So well, I'll probably bring it up some more, but N does not necessarily equal mg all the time. So, but for this case, it does. You know. So, but anyways. So now if we do the sum of the forces for this plate, then real quick. So if we do the sum of the forces in the y direction, and we're going to consider it the plate basically as massless, just because you know the mass of the plate is almost negligible compared to the weight of the person. So a lot of times the self weight of the system is already taken account with the scales, so they're really accurate. But for teaching purposes, we're gonna say it's negligible right now. So anyway, so if we do the sum of the forces in the y direction, that's gonna equal 0, you know, because we're dealing with static problems. And then we're gonna have basically k delta x plus k delta x, so basically 2 of them. And we're gonna say that the displacement of this spring is gonna be the same as this spring. So it's not, we're not gonna have one person, well, I mean, we're not gonna have the person putting more weight over here compared to here, you know. That's not gonna, we're gonna say that their weight is basically in the middle. So it's evenly distributed on this spring and this spring. So anyway, so these delta x's are gonna be the same then. So yeah. So anyways, so we have those guys that are heading in the positive direction, and we also have minus n. So yeah. So basically, in the end, if we add n to this side, we get n equals, so this is going to be basically just 2k delta x. And then, so in the end, so really this is just your weight. So we'll just say weight right now. So your weight is equal to your normal force. Your normal force is going to equal 2k delta x, you know, since there's 2 of them. So really, if you're able to figure out what your delta x is from all this, basically the distance that you've shrunk in this plate, you know, because technically the plate is going to be down here. And just almost draw this like this, freehand it real quick. So your plate is going to be down here now, so you're going to have like a delta x like that. So basically, if in the end, if you're able to figure out what delta x is, you can figure out what the weight of the person is. So and k, like I said, is given just because springs are tested out before they're put into their unit. So that you know specifically what the stiffness is of that spring before using it. So, but anyway, so yeah, so your weight in the end is just going to equal to k delta x. So you're basically given this. This is going to be measured, and then so if you multiply all 3 of these, then you get your weight. And that's just how scales work in the end.